Hi guys. In today's lecture I will be discussing the basics of VHDL language. Before I start, I'd like to say a quick thank you to my good friend Amit Katuria, who's a design engineer at Intel Corporation, for helping me make the slides for this lecture. So as part of today's lecture, I will be discussing what is VHDL. Then we'll be looking at the different types of design units in VHDL, and then we'll look at the different styles of modeling in VHDL in a very brief manner, because as part of this lecture we will be seeing the basics, but as part of this course we will be seeing all of these facts in detail. Okay, so let's begin. So what is HDL? HDL stands for Hardware Description Language. So if I break this phrase, it says it's a language to describe hardware. Typically, you have seen languages such as C and C++, where you write a program and you tell the computer how to manipulate or process data. But again, this is for software. In hardware, we know that there are different types of gates in digital hardware. You have AND gate, you have OR gate, you have XOR gate, then you have elements such as flip-flops, say a D flip-flop where you have inputs D and Q, output Q. You have T flip-flops, you have SR, JK, and all of that. So what if I want to write or describe a circuit that looks as follows? For example, I have an OR gate that feeds into an AND gate, that feeds into an XOR gate, whose output then goes into a D flip-flop. The output of the D flip-flop goes as one of the inputs to the OR gate, and then I have another flip-flop which is again a D flip-flop, the output of which goes into the XOR gate. This is A and this is B, and let's say this is output O. Now this is my circuit. This is a very small circuit, but imagine something 10 times the size of this, that has 10 OR gates, 10 AND gates, 10 XOR gates, and 10 flip-flops. I cannot draw this. The reason is it would consume a lot of time, and also it is not scalable. Scalable as in we cannot keep drawing bigger and bigger circuits. So for that, what do I do? That's the question. I would need a language that has some syntax or words that will help me describe a circuit like this. That is the fundamental need of why we need a hardware description language, is something that we can describe digital hardware with. Okay, so I hope this basic reason of why we need an HDL is clear. Now, when it comes to VHDL, VHDL stands for Very High Speed Integrated circuit HDL. So you can say it's VSiC HDL, or in short VHDL, very high speed integrated circuit HDL. Now there are two approaches to learning VHDL. Approach A is that we learn all the syntax up front, all of it in VHDL, look at the different components, and then we apply. Approach B is that we look at small parts of VHDL, look at examples, implement those examples, and then we move on to the next example. So we do this cyclic process, and hopefully we would have learnt the important parts that are needed for you to learn VHDL. Let me tell you that VHDL is a very big language, as in there is a lot of syntax, and it takes a good amount of time to master all of it. But as I again said, that there are the important concepts which if you learn, you should be able to design most circuits. Okay, so we will be taking approach B as part of this course. So if I take a VHDL design or a VHDL code, there are primarily 5 units. You have the entity, architecture, configuration, package declaration, and package body. The two most commonly used units are entity and architecture. I will also explain configuration and package declaration and package body, but as a part of this course we will be primarily looking at entity and architecture, and to a very small extent we'll be looking at configuration. You can say that 80% of the times you look at entity and architecture, 15% of the times you would look at configuration, and 5% of the times you would need a package declaration or package body, especially when you're a student or you're learning how to write VHDL. So let's look at the first unit, that is entity. You can think of the entity as the nameplate of the design. What do I mean by the nameplate? Let's take an example. That what if I would like to make a small circuit that has 2 inputs which are connected to switches. Let's call it switch 0, let's call it switch 1, and the output of the circuit, let's call this circuit X. The output of the circuit is connected to 2 LEDs or light emitting diodes, say LED 0 and LED 1. I'm still to define what happens inside here, but I know what are my inputs and what are my outputs. If I know both of these, then it's enough for me to say that I can write my entity, because my entity tells me who are the members in my house, or basically the nameplate. So again, to summarize, entity helps me define the input and output ports, and also specify what type of ports they will be. We'll see an example soon. So in my entity I specify switch 0, switch 1, they will be of the type input, LED 0, LED 1, they will be of the type output. Entity helps me specify this. Architecture, on the other hand, will help me specify what goes on inside this circuit. So, for example, if I would like to specify that my LED 0 must glow when my switch 1 is pressed, basically I would like to connect LED 0 to switch 0 and LED 1 to switch 1. This specification that LED 0 is connected to switch 0 and LED 1 is connected to switch 1 is done in my architecture. So, architecture tells me what or how my circuit is going to behave or function. Please understand, the entity helps me specify what are my inputs and outputs, but it's my architecture that will help me specify what my circuit is going to do. So now let's look at this example in a more formal way, or actually how it is written in VHDL. So a typical VHDL design looks like this. First, you have your library declarations, which are common for most designs. We will see different libraries as we take examples. But the important part here is the entity. In entity, you have a few keywords and you have a few user-defined words which you as the user can define in your design. The words in blue, as you see, are all keywords, and the words in black are user-defined words except a few, and I'll just point them out. So for example, the syntax is as follows. Entity, this name is, so this you can define. So let's say we give the name switches underscore LEDs. So entity switches underscore LEDs is switch underscore 0. These are user defined terms. Then you give the colon. It is of the type input, that is switch 0 is of the type input, and the data type or the type of port, it is an input port, but the type or the data type is standard underscore logic. Now standard underscore logic is a library which is a part of this library defined, which we will be discussing in a future lecture. But for now, please understand this once again, that my name of the port, the type of the port, and the data type that it will carry. Similarly, switch 1 is of the type input, again of type standard logic. LED 0 and LED 1 are of the type output, of the type standard logic. Please look at the placement of the semicolons. The last semicolon is outside the bracket. This is how the syntax is. This is syntax and must be followed. You don't have an option of not following the syntax. It's a language, so it has its own style and syntax. So then we say end the same name that you defined here. Let me go over this once again quickly. That is the entity. I first write the keyword entity switches is, then I use the keyword port, open bracket, switch 0, which is the name of the port, it is of the type input and the data type is standard logic. Then switch underscore 1 is of the type input and the data type is standard logic. Similarly, I'm sure you must have figured out LED 0 and LED 1. And then I say end with the same name that I used here. Please understand that this name and this name have to be the same. So this was an example of entity where I specify my inputs and output. Now, architecture, this is the format, this is an example. The format is quite straightforward. Architecture keyword, behavioral. This is a user defined term, you can define it. Of. This name and this name have to be the same because I have to make sure that my architecture is belonging to this entity, hence both the names have to be the same. That said, I use the keyword begin and then I would end the architecture with the same name that I gave it, which would be behavioral here. So this was the general format. Now let's look at an example. Architecture behavioral of switches underscore LEDs is, which is the same name that I gave here, begin. As I said, I wanted to connect switch 0, switch 1, LED 0, LED 1 to each other. So that is exactly what I have done. I have taken switch 0 and I have assigned, please understand this term, we'll be using this very frequently. I have assigned switch 0, or the other way around, I have assigned LED 0 to switch 0 and I have assigned LED 1 to switch 1. The assignment statement is this in VHDL. This is the most commonly used assignment statement. In the future we will see another assignment statement like this, which is used for variables, which we will see as part of a future lecture, but for now, when we have to use assignment statements, we'll be using this one. So this was a very straightforward example of an entity and an architecture. Now I would like to mention a quick point here is that if I have one entity, I can map multiple architectures to the same entity in the same VHDL design. As I said, that your VHDL design can have only one entity, but it can have multiple architectures. Okay, so the question that might come to your mind is, how does my entity know which architecture to look at? That's a good question to have. The answer to that is that I specify that in my configuration file. In my configuration part of the VHDL design, I specify which entity maps to which architecture. Since I have only one entity, then you will specify which architecture is used for that particular entity depending on certain conditions. Okay, so that leaves us with package declaration and package body. Now suppose if I would like to make my own data type such that we looked at standard logic, standard underscore logic. Now I would like to specify my own data type, my own input output ports which are globally used. Then I would do all of that inside a package. I would not like to go into further detail of package declaration and package body for now, but as I said, 80% to 15% of the times we'll be looking at entity architecture and configuration. I hope that the basic introduction of entity and architecture was clear. So let's look at another example which you're more familiar with, which is a half adder. As you know that a typical half adder has 4 ports, 2 input ports and 2 output ports. The 2 input ports are A and B. The 2 output ports are sum and carry. As I said, the entity helps me specify the inputs and output ports. That's what I have done here. It is same as before. Entity half adder is, this was a user defined term, so you or the user has decided to give the term half underscore adder. Entity half adder is the keyword port, the 2 ports A and B, A comma B, of the type input. Now previously we saw the data type standard underscore logic, but here I'd like to introduce another data type which is of the type bit, bit. Basically the bit data type can take only 0 or 1, no other values. We will see in a future lecture that the standard logic type can take more values, but for now just understand that the bit data type can take the values 0 or 1. Similarly, the outputs sum and carry are of the type out, which we know, of the data type bit. Again, end the user defined term half adder. So as we know again that entity helps me specify only the ports of the design. Now the architecture is what we need to look at. This is the hardware that we want inside a half adder, so we would hopefully specify this as part of the architecture. Now to specify an architecture, there are 3 styles of modeling. There is the structural style of modeling, there is the data flow style of modeling, and then there is the behavioral. You use structural and data flow when the internal connections are clear and straightforward. This is typically used for smaller designs. For larger designs, you would describe the behavior of your design so that then the VHDL compiler or the VHDL translator understands that what design you are expecting. But as a student, you will understand that you will use a combination of 1, 2 and 3, which is the most commonly used combination. Is you would build bigger designs using behavioral, connect them using structural and data flow. And as part of this course, we'll be looking at all 3 examples. For now, let's look at the half adder using the structural and data flow. Now, as part of my structural design, again, please let me be clear that the entity would be the same. There is no different way of writing the entity. The entity is always the same. Let's look at the structural style for a half adder. So architecture, again, user defined word of half adder is, first what do I do before I begin? I first declare components. I write components defining a XOR gate and an AND gate. Remember, the style of modeling is structural, so I will define different structures which are components. I will specify separate, please understand, in structural we have separate VHDL designs for an XOR gate and a separate VHDL design for an AND gate. So let's look at it from this perspective, that I have an AND gate design, I have a XOR gate design with 2 inputs and an output, and then I combine these AND gates and XOR gates as a part of a larger VHDL design, which then gives me A, B, I give A here, B here, I give A here, I give B here, and I take output, and then I would say that the XOR gate would be the sum and the AND gate would be the carry. Now this is the structural way of looking at it, where I will define different components. Component XOR 1, which has ports P and Q as inputs and R as output. Similarly, component AND gate has X and Y as inputs and Z as outputs. So let's look at this. I would have P, Q and R. Similarly, I would have X, Y and Z as my individual components of my XOR gate. And then what I do is I would say, okay, my carry will connect to my Z, my sum will connect to my R. So I use the keyword port map, which will map the ports A to X, which will map A to X, B to Y, similarly A and B to these two, and carry to my R. Just for your reference, we'll be looking at this in the future. Don't worry, we'll be looking the structural style of modeling in great amount of detail in the future. This is called positional association, where I am associating each port with its position where specified in the entity. Again, it's just a basic introduction. We will be looking at an extensive example in the future. So this was the structural style, where I specify the structure of my VHDL design and I write my architecture in this way. As you see that this is a much longer VHDL design, but it helps me connect smaller designs into a larger design. That is when I will use the structural style of modeling. We will see an example in a future lecture, so do not worry about this. The second style is the data flow style. For the half adder example, this is actually the best style because it's very straightforward. If you see, architecture data flow of half adder is begin, my sum is A XOR B, my carry is A and B, and then I say end data flow. As you see that this was the user defined term, but this term has to be same as my entity. I use the keyword begin, I use the keyword end, and then I just specify the data flow, which is A XOR B, which is assigned to sum, carry gets assigned A and B, XOR and AND are keywords which will then specify a XOR gate or an AND gate. So it's a fairly straightforward style of modeling. For very small designs, the data flow style of modeling is a perfect match, but for larger designs we will use a combination of all three, which is the behavioral, data flow and the structural style, and we look at different examples. So the hardware was simple, that sum is A XOR B, carry is A and B, and that explains the data flow and the structural style of modeling. We will look at the behavioral style a little differently in the future lecture, hence I'm not discussing the behavioral style now. Thank you for following today's lecture. In today's lecture, we understood the basics of VHDL, of how to specify an entity and architecture. We understood the configuration that you can have one entity but different architectures, and we saw that there are three styles of modeling, which is structural, data flow, and behavioral. And in the future lectures, we will see each of these models very carefully. We will look at more syntax related points. We will look at the concept of signals as well. So stay tuned for the next lecture. Thank you very much.